Good morning, everyone. We are Group 10. Today, we are going to present our project, Elevator Controller System. This slide shows our group members. Everyone in the group took part in the system design, logic planning, and the simulation work. Now our projects focus on the designing an electronic lift controller using digital logic and this simulation software. It shows how combinational and sequential logic can be used in a real-life control system. In real life, a lift cannot be controlled manually. The system must automatically decide when to move, which direction to go, and when to stop. These are the main problems that our project aims to solve.
Moving on to our suggested solution, to solve the problem of manual operation, we designed a fully digital lift controller that combines two core logic types. First, we utilize the combinational logic such as comparator and clock enablers to make real-time decisions. Second, we integrate sequential logic, specifically a 3-bit up and down counter, to act as the system's memory and to track the current flow. By integrating this, the system can intelligently decide when to start, when to stop, and when to change the direction. Next, we define the critical system requirement to ensure the lift operates safely and logically. We established 4 main rules. First, safety interlock. The lift is strictly prohibited from moving unless the door is confirmed closed. Second, the direction control. The system must automatically determine whether to go up or down based on the target flow. Third is precision stopping. It must detect when the current flow equal to the target flow and stop automatically. And for the last one is floor limits. Crucially, we implement logic to prevent the lift from crashing, meaning that it can count below floor 0 or above floor 7. And for the lastly, for the system implementation, we translate this requirement into a simulation using DIT software. The core of our design relies on 3-bit saturated counter. We chose saturated design specifically so that if the lift reach the top floor, which is floor 7, it stays there rather than rolling over to 0. We also implement a comparator block to handle the floor matching and the clock enabler control to physically drive the motor only when safe. Now I will pass to the next speaker.
Hi, I'm Lin Zhiting. Next is my part. And look this line. Each state in the state transition diagram represent one flow from 000 to 111. When the enable signal is active, the counter move up or down based on the declaration input. At the lowest and highest flows, the counter stays to prevent overflow. This slide shows the complementary circuit design implemented in this. All modules are integrated into one system. The preset and the next state table define how the system transition between states and the special the required T flat flow improves.
So to reduce circuit complexity, Carnot maps or K-maps were used to simplify the logic equation. So the variables involved are x, q2, q1, and q0. So for each t, which is t2, t1, and t0, it has been mapped and minimized, resulting in the following Boolean expression. So the first one is t0 is equals to 1, and t1 is equals to x exclusive or q0. And so for the t2 is equals to x bar q0 q1 plus x q0 bar q1 bar. So a comparator design. A comparator A comparator is used to compare the current floor with the target floor. When both values are equal, a stop signal is generated.
The clock-enable logic ensures the counter only operates when movement is required. Once the target floor is reached, the clock is disabled. Additional safety features include door close input, password authentication, and emergency override. Simulation results show that the lift moves correctly according to the selected direction. The system stops automatically at the target floor. To conclude this project successfully demonstrates a functional digital lift controller, and the future improvement may include circuit simplification and to support more flows, and lastly to add more safety features.